Thank you, Rajat, for the introduction. And typically when I teach, I tell them that if you cannot hear me from the back, please let me know. But since I'm using a microphone and I have a very loud voice, tell me to shut up if I have to shut up. Okay, so thanks to the organizer, firstly, for inviting me to give a talk. And actually, I changed the title and abstract in the middle because I thought that the phrase applied probability has all different meanings. And I'll talk about something. I'll give applications of probability to pure mathematics, so-called pure mathematics. So this will be an application of probability to dynamical systems and a bit of number theory. But still, it is applied probability, in my opinion. So, okay, so this is a joint work with Anish Ghosh, who is a collaborator, who's from TIFR Mumbai, is a collaborator of mine. And then another person is Maxim Kirstebum from University of Hamburg, who's doing a postdoc there. And both of them are actually ergodic theorists. And Anish invited Maxim, who's supposed to be an expert in extremes of dynamical systems. He did his PhD in that area, and then we started working, and he gave us a problem. He gave us a problem which we solved, and then we realized that that problem has been solved already. Then we just changed the problem and solved that. Okay, so this paper is going to appear in this journal, Ergodic Theory and Dynamical Systems. I'm personally very excited to have a paper there. It's a good journal in ergodic theory. Okay, so I'll start from something very basic, so basic that we do it in middle school. So we start with this rational number, 7/24. What you do is you write it as 1/24/7, and then you expand this as 3 + 3/7. We do this a lot. We do the reverse thing, actually. So we are given this guy, and then we are supposed to simplify it to 7/24. I'm just reversing whatever we have done in elementary school, maybe middle school. And note that I'm using colors, and then by the way, this I'll denote as 3, 2, 3. We'll see why later. But then note that I'm using colors, and this 7 is strictly bigger than this 3, and 3 in turn is strictly bigger than this 1. What do I mean by that? So I mean by that is that this 3 is obtained because of a remainder when you divide by 7. That's why this is strictly bigger. Similarly, this is a remainder when you divide by 3. So therefore, just this example, reversing our middle school arithmetic, tells us that by Euclidean algorithm, which is of computation of GCD of two numbers, any rational number p by q of the reduced form, which has GCD 1, will have a terminating regular continued fraction expansion. This is called the regular continued fraction expansion. Because every time you're going to reduce this number, and then finally, because remainder is always strictly less than the number you're dividing by, so then it will finally has to go to 1, okay? So there is no choice here. So any rational number you start with, you apply this algorithm, you're going to stop, you're going to terminate with a regular continued fraction expansion. This is called a regular continued fraction expansion of a rational number, okay? Interestingly, if you start with, say, 4 numbers, which are natural numbers, by the way, all of these are natural numbers that you're getting here, right? Because you started with 2 natural numbers. So you start with a positive and less than 1 rational number. So, number from the, sorry? From this expansion, you can recreate the original number? Yes, of course. Yeah. That's what we do in middle school, yeah. So whenever you have A1, A2, A3, A4 in N, I define this guy to be this number. And you can check that this is a rational number, because these are all natural numbers. You can just, again, whatever we do in middle school, you can do that to show that this is a rational number. More generally, if you look at A1, A2, AN, just extend this whole thing up to n terms. By induction on n, this is a rational number. Okay? So what I have actually shown to you is the following. It's a theorem. I actually don't know whose theorem it is, very classical. So it says that any number, omega, I'm writing omega, there is a reason, because this is a probability, there's some probability connection. In 0, 1 has a unique non-terminating continued fraction expansion if and only if it's irrational. So I showed that if it is rational, it will stop. If it stops, it is rational. So therefore, you'll have a non-terminating continued fraction expansion in the same algorithm that we did, okay? If and only if it's irrational. This is I have shown, but this is something I have not shown. Furthermore, in this case, you can show that the nth truncate of this, if you stop it, say at here, and then don't do anything, that will converge to omega as n goes to infinity. You can do some estimates, some hard estimates, and show that this is the case, okay? Okay, so this is actually gives you a canonical rational approximation of omega, okay? If you just stop at a large enough n, you actually don't have to stop at a large enough n. Even at a small enough n, this gives you good approximation. Two such examples. We do it, again, middle school. Pi is approximately 22 by 7. I think this is the second or third approximate of pi. And then if you go 2 steps further, you get this number. Anybody knows this approximation? You write 113355, cut it here, and then you do 355 divided by 113. That is an approximation of pi. I have to go two more steps in the continued fraction. So these are essentially, that's one of the uses of continued fraction. And how good is an approximation is actually a number theory question that has connections to, I think it's called goodly approximable or badly approximable. There are some terms in ergodic theory. Of course you do better. But the point is, how fast are you doing it? That's a question in ergodic theory. Anyway, I'm not going to go into that. I'll just say why continued fractions, and here is my contribution, here is my connection to Vedic mathematics. So the first one was done by, first work in this area was done by Aryabhata in this work, in this book. He solved some equation using continued fractions. So whenever I apply for a grant, I'm going to use this. Okay, so. And is that the year in which you published? Actually, yes, according to Wikipedia. According to Wikipedia, yes. What's the serious question? Yeah. So as far as I understand, it's 5th century. Whether that's the year is not really known, but Wikipedia says 0499, and whatever Wikipedia says or Google says is true. We know that, right? So, okay, so continued fractions have canonical connections to various branches of mathematics. Today we will see naturally ergodic theory and probability theory, and a bit in the end perhaps hyperbolic geometry and number theory, but not too much maybe. These two would be the main. But it has connections to combinatorics, analysis, algebra, various things, okay? So it's a very important topic. If you want to learn more about it, this definitely is the correct year, okay? So look at this monograph by Kinchin. It's a classic, okay? So this is not just Wikipedia. I know that, I've seen the book. Okay, so I'll talk about something called Gauss dynamical system. So this will relate to Gauss also, not just Aryabhata. So let's first look at what we did. Let's go back. We started with an omega. He wrote it as 1 over omega. And then we wrote 1 over omega as its integer part and its fractional part. That's all we did in the rational number that we started. So again, elementary school or whatever, middle school stuff. I'll call this 1 over omega box part, the integer part, as A1 omega, and 1 over omega integer part as T omega, okay? And I can do that again on T omega now. Whatever was omega, replace it by T omega and do the same, play the same game. You apply A1, so essentially T omega you write at 1 over T omega, and then you do the same, play the same game and repeat, okay? So that will give you the next step, and so on. You'll go on. This A1 of T omega, so whatever you did for omega, you do it for T omega, I'll call it A2 omega, and this will be, of course, T square omega. And this will go on. This is the algorithm of finding regular continued fractions of a number. Now the point is, the moment you start with a rational, at some point you'll stop this. Otherwise you'll have to deal with 1 over 0 and so on. You'll avoid that, you'll stop. But suppose it's not rational, then you go on forever. Okay, so this gives us what is called the Gauss map, or the Gauss dynamical system. So you start with omega, capital omega is 0, 1. You'll take small omega from capital omega as we do in probability. And of course we need a sigma field, and which other sigma field can we think of other than the Borel sigma field, so we'll do that. Define the map T and omega exactly the way we did it. So T omega would be 1 over omega, the integer part, and this is the, what is it called? The fractional part, thank you. This is the Gauss map, by the way, and this is the integer part, this is the A1 map for irrational omega. And now you would ask me, what about rational omega? Do whatever you want, okay? Because we are going to put a measure which is going to have probability 0 on the rationals. So for all j, now you set aj plus 1 omega to be a1 of tj omega. Okay? So this is precisely what we had there. So a2 is essentially what I am saying is a1 is something, then a2 is just a1 compose t, a3 is a2 compose t, and so on. This is what I'm writing like that. Okay? So I'm just repeating the procedure. It's a recursion in some sense. And then what I'm saying is almost all omega, which means actually for all irrational omega in this case, omega has the infinite, non-terminating continued fraction expansion like that. Okay? So far, we are talking about a measurable space, not a measure space. Why? Because there is no measure yet. Okay? Because this is just omega and a, no p yet, or no mu yet. We'll talk about it. But a quick observation is that these maps are measurable, very easy to check. T and A1 are measurable. This can be given not as an elementary school exercise, unfortunately, but definitely the first exercise in measure theory, right? Well, not first, maybe 7th class. Which in particular tells that each AN is measurable because you're just iterating things. Okay, so far so good, but we need a probability measure. Otherwise, why am I talking applied probability here? So let's look at this. So let's go back quickly. Omega is 0, 1, and T is this map, A1 is this map. Bad news is that T does not preserve the most important probability measure on 0, 1. Sorry, guys. But any bad news has to be followed up by a good news. So here is the good news. You define a probability measure. This is called Gauss measure. I didn't even know that this is called Gauss measure. It's not Gaussian measure, Gauss measure, on this same probability, measurable space by just taking this at the Radon-Nikodym derivative with respect to the Lebesgue measure. Okay? So this log 2 is just to make it probability measure. Otherwise, it won't be probability measure. Okay. Gauss proved that T preserves P in the sense for all T A, which is measurable subset of 0, 1, P of A is P of T inverse A. This is a theorem of Gauss, actually. And unfortunately, I don't know the exact date, just before you ask. I tried. The thing is that even whether he ever wrote a proof is a question. He just thought of it from somewhere. Okay, so this thing is called a Gauss dynamical system. By the way, any measurable space, any measure space, in this case probability measure space, with a measure preserving transformation, this quadruple in ergodic theory is called a dynamical system. In this case, it's Gauss dynamical system. It's a very important dynamical system. I'll try to convince you towards the second half or third part of the talk, third quarter of the talk. Okay, so anyway, so is this notation clear? So you don't have this, the most natural measure is not preserved, and hence we go for slightly unnatural measure, but not so unnatural. After all, Gauss thought about it. Okay? So then, here is the next section, and this is what is called extremes of continued fractions, and I'll talk a little bit about Wolfgang Doeblin and his life, okay? Quickly. And I'm honored that my work connects to Aryabhatta, mostly that, Gauss, and also, most importantly actually, Wolfgang Doeblin. Okay, I'll tell you why. Okay, so what is extremes of continued fractions? Roughly speaking, this is where it started. Doeblin in 1940 guessed that exceedances of digits, I'll tell you what it means, okay? In the continued fraction expansion of a number chosen randomly from 0, 1, according to Gauss measure, should have Poisson asymptotics. I'll tell you what it means. It's just a big sentence right now. Just bear with me for some time. However, unfortunately, the proof was completed at the backdrop of World War II. And I'll tell you exactly more precisely what he was doing then. But then, of course, it's a pity, but it had a subtle error, which was later fixed more than 3 decades later by Srivastava. The error was very subtle, and I think there was some uniformity in some convergence which he was not uniform. He thought it's uniform, so it has to be bypassed by some compactification argument, some such thing. I forgot exactly what it is, but I can always go back and check. So unaware of Doeblin's work, which was very esoteric because, you know, I don't know where he published it, but it was kind of an esoteric journal, and during the World War, everything was sort of lost. People didn't really care about the work and so on. Galumbus actually investigated the asymptotics of the maximal digit. See, again, I'll tell you what it means. It means roughly if you choose an omega at random from 0, 1, according to the Gauss measure, look at its first, if you choose it at random, then it's with probability 1 and irrational, because this is equivalent to, this measure is equivalent to Lebesgue measure, Gauss measure. Now, it has an infinite expansion, regular continued fraction expansion. Look at the first n digits and look at their maximum. How does it grow? So this is the question that Galumbus answered. Actually, this follows from Doeblin's work, had it been correct, but unfortunately it wasn't. So officially speaking, this is the first correctly proven results on extremes of continued fractions. After that, there were explosions of work in this area. So much so that whatever problem we first attacked actually had been solved, we didn't know. Okay, so you can see, this is just to mention a few. In fact, some of these papers have come in very good journals. For example, the Samur paper had come in Transactions. And one of the Philippe paper, I don't know whether I mentioned that one, but I'll mention it later, came out in Duke Math Journal. So these are like really good math journals where these papers came up. And it's still an active area, as you can see. So, little bit on Wolfgang Doeblin, a little bit fast now. So he was a French-German mathematician, was caught up in the World War II. And he was actually working in a telephone exchange, if I remember correctly, and proving results about Poisson process. And anyway, so in 1940, he actually sent a sealed envelope from the war front to the Academy of Sciences in Paris. And he had to unfortunately commit suicide in 1940, later in June. And for legal reasons, because he passed away, and it only could be after 60 years, it could be opened. And one of the people who opened the envelope was Yor. And what he realized, it was written in a very old-fashioned form, but he actually had an advanced representation of one-dimensional diffusion and many other things. In particular, he had a version of Ito's lemma for that setup. And therefore, Ito's lemma is now called Ito-Doeblin theorem by many mathematicians. When I say many, I mean definitely French. And I think not just French, any reasonable mathematician should call it Ito-Doeblin theorem. Because Ito did it afterwards. At that time, Ito didn't know about Doeblin, of course, but he did. By the way, all this information is nicely written and also mathematically nicely, a paper by Bru and Yor. This is Yor. And this came out in Finances and Stochastics, if I remember correctly. And by the way, this is a movie. You should watch it. This was once shown in ISI Kolkata. I don't know, you were there that time, Rajat? No, most probably not. Bangalore also, okay. It's a very nice movie, actually. Anyway, so now I'll talk more math, less melancholic story. So what is Doeblin-losifescu asymptotics? So let's go back to the notation now again, because by now we have forgotten it. So we start with omega, which is 0, 1. We take this measure, these are the measurable sets, these are the events. I define the measurable maps, which are the Gauss map, 1 over omega fractional part, and integer part respectively. And we know that it doesn't preserve the Lebesgue measure, but it does preserve the Gauss measure, which is this, and then therefore this is a dynamical system, which we are calling the Gauss dynamical system. Now, by the way, this theorem of Gauss, which I could never see where Gauss has proved it, I think he just knew it from somewhere, and it can be given as a very elementary probability theory exercise. So I call it a probability theory 2 exercise, the moment you do distributions with densities. So if x is a random variable having a probability density function, this is a valid probability density function because it integrates to 1. Just show that if you take the Gauss map on it, that also has the same density. It's not hard, it's difficult. I actually gave this exercise to my students in ISI, and the good students could do it. I just told them this is the theorem of Gauss, and they all got motivated. Okay, so anyway, so let's go back to the notations once more, because I need to tell you what those ANs are and so on. Omega is this is the measure, and then I define the maps as usual, and then I define AJ plus 1 to be this guy. So this defines a sequence AN of positive integer valued random variables on this probability space, because everything is positive here. Because the 0 will only come when omega is rational, and we are eliminating that. That happens with probability 0. What is AN? To be honest, AN is just the nth digit in the regular continued fraction expansion of a random number generated according to the law P. So maybe I'll write this down. So you choose omega according to, maybe I'll write a little bit, according to P, which is Gauss measure. Tell me if I'm writing too small for the people at the back. Okay, and then you just write omega, the expansion of omega you write as A1 omega, A2 omega, and so on. Okay, and of course for rationals you don't care because that happens with probability 0. So essentially for irrationals you're writing it. Okay, so now the point is T preserves P immediately implies that AN is a strictly stationary process. It's just a restatement of stationarity. In particular, what is going to be important in the next slide is that A1, A2, A3, etc. are identically distributed. One comment I would like to make is that you can prove, which is not important for me, but since it's a probability crowd, AN is just a Markov chain, taking values in 0, 1, and its stationary distribution is just Gauss measure. Therefore, if you start from Gauss measure, this sequence is going to be ergodic, obviously. In fact, we will use the fact that it's exponentially mixing. So, Shubhu, you're talking about, is he? Okay. Anyway, yeah, you're talking about exponential ergodicity. I'm going to talk about exponential mixing. You need a bit more in the proof. Okay, so why is this identically distributed important? Because now I'm going to only talk about some probabilistic properties of A1. Same applies for A36 as well. Okay? Okay, two easy observations without proof. By doing brute force computation, you can show that the tail of A1, by the way, A1 is an integer valued random variable, right? It's a positive integer valued random variable. You take an integer, you look at the tail of A1, this behaves like 1 over m up to a constant. You can explicitly compute and then show that this second part is easy to show, but of course this needs a bit of computation, but not a very difficult computation. The advantage is that A1 has a very easy explicit form. You can directly do it. And once you do it for A1, you know it also for A36 because of the identically distributed property. In particular, A1 has a power law distribution. I'll make it more precise. If you take any u bigger than 0, you look at A1 log 2 by n bigger than u, this is going to behave like 1 over un for every fixed u as n goes to infinity. Okay? Which means n times this guy is going to go to u power minus 1. And this is what is called regularly varying with index 1. Your talk had some regular variation in it, right? So this is essentially, this tells you that all the AIs, all the digits of once you choose omega according to the Gauss measure, all the digits have regular variation with index 1. So that brings it to extreme value theory and heavy tails, essentially, because this is heavy tails, with tail being 1. Okay, well, I'll use this observation now. I told you A1, A8, A2, AN, etc. are identically distributed. Suppose they were also independent. Then they will be IID, right? Then, of course, indicator, you choose a UN, okay? You choose a U, fix a U, and then look at A1 log 2 bigger than UN, A2 log 2 bigger than UN, A3 log 2 bigger than UN, and so on. These are going to be IID as well, with functions of the A1, A2, AN, etc. And they will be Bernoulli with parameter Pn, where Pn is this guy, because all of them they're identically distributed. I can just as well work with 1. Now, I know that this is n times Pn is going to u power minus 1. I just told you in the previous slide. Therefore, for all u positive, for all fixed u positive, if you look at the number of exceedances of the digits, I'll write this down for you. So, E for exceedance, Un is defined as number of digits in the first among the first n digits which are bigger than n by log 2. Okay, this is my definition. This is nothing but sum of these indicators, of course. And some of these indicators, if these things are independent, this would have followed binomial. So I'm writing blue here, and blue here to say that these are not true, I'm faking it. Okay? However, if this cheating is allowed, then this would be binomial, and n times Pn converges to u power minus 1. So but we know, therefore, this should converge to Poisson. Okay? So epsilon u infinity is basically you're taking limit as n goes to infinity follows Poisson with parameter u power minus 1. Let's write these things down. I'll leave them. So by the way, so coloring is very indicative. Sorry? U inverse, yeah. Oh, that should be u. Yeah, thank you, thank you. N is gone because you've taken the limit. Thank you. That's what dyslexic. I wrote opposite side, sorry. Yeah. So then this is a combination of this and this. The color combination tells you that red and blue together implies the violet thing. However, I'm still cheating because this blue thing is not 2. But that doesn't mean this won't be true. And it is. That's exactly Doeblin's work. So Doeblin guessed rightly and almost proved that this exceedences has Poissonian asymptotics as n goes to infinity. And then he's, of course, had a mistake which was corrected by Losifescu. And as I said, without knowing Doeblin's work, Galambos actually showed that if you look at Mn1, there's a reason why I'm calling it Mn1, because later on I'll look at kth maximum. The maximum among AI log 2, the log 2 is there because of that Gauss measure. It's coming from inherits from the Gauss measure. It makes things a bit cleaner. That's why I'm keeping the log 2 here, so that I can divide only by n. You look at the maximum of the first n digits multiplied by log 2, that goes to, after scaling by n, a Fréchet distribution, extreme value distribution. That's expected because these guys had power law tails with parameter 1. Only thing is that they are not independent. I cheated there, right? But independence is there in the sense of mixing, and therefore this will still go through. This is just a restatement of probability of this guy is equal to 0 going to this guy is going to 0. But Galambos didn't know that because this paper wasn't known and there was a mistake as well. So therefore, this is the first correctly proven result in extreme value theory for Gauss dynamical systems or continued fractions. Okay, so what is our contribution? So look at the Doeblin-losifescu asymptotics. The question that we can ask is what is the rate of convergence there? And we are going to answer that question. Before answering the question, let me tell you why it is important to answer that. So firstly, once we answer that question, okay, I have to make it precise, what do I mean by rate of convergence, with what metric and so on, but we'll do that. Once we do that, we can estimate the rate of convergence of the scale maxima sequence in the Galambos convergence. This actually, once we do that, will actually significantly improve the result of Walter Philipp, who actually, and it betters an error term in his proof of a conjecture of Paul orders. So this was an important thing in his proof, so which actually is improved now. I'll tell you how improved it is in the next slide. Now, not just the maximum, we can talk about the rate of convergence of the kth maxima of among the first n digits. And this is going to be uniform over k. We can do an uniform the bound over k. A tiny detour of our proof actually recovers a result of Tyrod-Kamishka on the weak convergence of the corresponding extremal point process. What do I mean by that? So I'll quickly write it down here. I'm not going to do a lot of fuss about it because I'm going to sort of avoid that. So basically what you do is you look at AI log 2, you divide it by n. That's your ith digit rightly scaled. You put Dirac delta measure on this whole thing and take sum from 1 to n. So this is the extremal point process, and one can show that this converges weakly to a Poisson point process. And that's just a detour of this. And this was inspired by a work of Rajat and his co-authors. And interestingly, it has number theoretic consequences. I'll tell you some consequences if I have time. Let's see. Okay, so the rate of convergence of the scale maxima for the geodesic flow on the modular surface, this is something coming from hyperbolic geometry intersection with number theory, can also be obtained. If time permits, in the end, I'll talk about this. So it connects to various things, and therefore this is an important problem. So this is our main result. So what is the main result? If you look at, so the distance is the total variation distance. If you look at the distance between this guy and this guy, this is approximately binomial, except that things are dependent, and this is Poisson. So the distance between the approximate binomial and Poisson, this exceedance and the limit, the total variation distance is bounded by more or less 1 over n, except that there is this ln, which is definitely slower than log n, but bigger than 1. We actually have a implicit expression for ln, just like Rajat had. So we have an equation that ln solves, okay? And then you can show easily that ln is at least going slower than log n. And therefore, essentially, up to a compromise of log n, we have more or less proved 1 over n. Okay? Yes, I'll talk about that soon. That's a good question, very good question. And of course, dependence on u is also there, which basically means that if you take any interval which is bounded away from 0, this is basically, this bound is locally uniform. Okay? So, okay, uniform essentially, uniform on those kind of sets. Anyway, so if you look at the kth maximum among the first n digits, suitably scaled, then you can show that this supremum, so uniformly, this, by the way, this guy converges to this can be shown, okay? Not difficult. This uniformly, this is bounded by the same thing. This kappa is the same kappa, by the way. Doesn't have to change anything. It's basically comes from the fact that you're using a very strong distance here, okay? So that's why you get this uniformly. Okay, so comparison with the existing results, answering the question of Shiva, if things were independent again, A1, A2, etc., then the best known bound for the maximum is order 1 over n. This was proved by Resnick and Dehaene in 1989. Our upper bound blows pretty close to that. It's log n over n, and you can't blame much because there is a dependence here. So you can't do much more perhaps. And Walter Philipp for Gauss dynamical system showed that this distance is actually this order. Now, this may not mean anything, but this is a slowly varying function of n, in the sense that it is like 1 over log n. It's going to 0, but going very slowly to 0. It's not exactly like 1 over log n, but it's going to 0 very slowly. There is a precise way of saying what is slowly varying. Ours is definitely much better than that, because we have a polynomial term there, 1 over n. ln may be slowly varying, but it's basically regularly varying with 1 over n, n power of minus 1. Yeah. So that's what we have got. So we definitely improved it quite a bit, and this improves essentially an error term in his proof, as I told you earlier. Okay, so this answers Shiva's question. So now I'll do a bit of sketch of proof, and then in the end, if I can connect with other branches of mathematics, I'll do that. Okay, so yes, I'll tell you. It will be part of the proof, last step of the proof essentially. The way I present it, last step meaning the way I present it. Yes, thank you for the question. Yeah, so the sketch of proof, the proof would need techniques from ergodic theory and what is called hard analysis, and I call it applied probability because I'm using Chen-Stein method. To me, Chen-Stein method is applied probability. Okay, hard analysis is not hard. It's not difficult. It's just we need hard estimates. Okay, it's not soft estimates as opposed to soft estimates. Okay, so I'll tell you. Okay, so what is the idea of the proof? Recall that this exceedance, which is written here, is just a sum of the Bernoulli random variables which are possibly dependent. Well, they are dependent, but not weakly independent, I would say. So weakly dependent, rather, I would say. And then, in some sense, I'll make it precise. Therefore, this is approximately binomial with n comma Pn, where Pn is this guy. And on the other hand, this guy is Poisson. I want to show what is the distance between this guy. Most natural thing to do would be to define an intermediate random variable. So you go a little bit from binomial, go to Poisson, but with parameter n times Pn, preserving the expectation. Okay, so that's the most natural thing to do. Define an intermediate random variable, which I've kept intermediate between these two, epsilon tilde un, very bad notation, sorry, which is Poisson. We take this Poissonian thing, but n times Pn. And let's just use triangle inequality. The total variation distance between these two guys is bounded by these two and these two. Bound, the first term is a crucial term. Bound the first term, one binomial and Poisson, not two Poisson, one binomial and Poisson using Chen-Stein method. And very specifically, I'm going to use the work of Aratia, Goldstein, and Gordon, 1989. And I'll use what Sandeep was asking, some exponential mixing that comes off. Firstly, it came off the paper of Philipp in 1970. He did it in context of number theory. This is a Duke Math Journal paper, by the way. Anyway, so I'll talk about it again more precisely. This is the way, so this is the probability and this is the ergodic theory component. Together gives you the bound on the first term. Second term is an error term, and you estimate it using what is called second order regular variation. So regular variation is a limit property. What is the second order correction? That is second order regular variation. So that needs a bit of hard analysis, that's all. As I said, hard analysis just refers to hard estimates, not difficult analysis, okay? Yes, exactly. How close n times Pn is to u power minus 1? That's all, that's second order regular variation, yeah. Okay, so as Remco already said, if you take two Poisson distributions, two Poisson random variables, their total variation distance because of lemma 8 of Friedman can be bounded by the distance of their expectations. These are very soft bound, they are much better bounds. This can be even given after the definition of total variation distance. My guess is that this can be given as an exercise in probability theory 1. Yeah, this is not difficult at all. It's just one small trick is there. This is a soft bound. Then you need a hard bound. How close this is to that, as Remco said. So basically this guy is just this guy. So you need to bound this guy. And this is what falls under the domain of second order regular variation. So more importantly, this is a very specific example. You just do brute force Taylor expansion. Okay? That's why you hard analysis. It's not hard, it's just you have to be patient. You should not do it at 8 p.m. in the evening after having a few bottles of vodka. Okay, that's the idea. Okay, so this is the second order regular variation bound, and this would be smaller. That was ln over n, and ln is log n. Okay, less than log n, but going to infinity. So this is smaller than that. So therefore, this is a correction term. Therefore, this is just a correction term. Done. The actual term is this guy. So you have, recall, this is just this exceedance. So this is a sum of these indicators, and this is a Poisson. So I'll deliberately introduce this notation that would be important for the next slide while I do it. This index set I would be 1 to n, okay? And then what you have, indexed by I, you have random variables xi, which are these indicators, which are Bernoulli Pn. Each of them is a Bernoulli Pn because of the identically distributed nature of the AIs, but they're dependent. And epsilon nu is just the sum of the xi's, I running over this index set n. Forget that index set I has n in it, forget that, let's just write I. Okay, now take y1, y2, y3, etc. IID Poisson Pn, okay? Then of course, if you look at epsilon n u tilde, which was Poisson n Pn, has the same distribution as summation of yi, I running from 1 to n, right? Sum of n independent Poisson, IID Poisson is n times lambda, right? So that's what I'm using here. So therefore, this guy I'm writing as sum of Poisson, but the point is these are independent Poisson. I didn't write that, stress that here, but these are independent Poissons. Here there are dependent Bernoullis. So I'm going to compare a sum of dependent Bernoullis with a sum of independent Poissons, which have the same mean. So this is what I need to compare. Sum of xi, sum of yi. Question is how to compare that. And this falls in the domain of Chen-Stein method. More precisely, this is the setup. So I'll do a little bit of digression in notation, but I'll come back to it. Aratia, Goldstein, and Gordon, in their work in 1989, Annals of Probability, what they showed is this. Xi following Bernoulli pi I, possibly dependent. Now I'm stressing the independence here. Yi following Poisson pi I, same, not necessarily IID, but these are independent, okay? Then, this is the thing. For each I, suppose there is a subset Bi containing I, so there is a neighborhood of I, where Xi is such that Xi's are going to be nearly independent of whatever is beyond Bi. So this Bi will be called neighborhood of dependence. So roughly speaking, for every point here, so I'll erase this part here. So roughly speaking, for every point here, you're going to, suppose this is your Xi, yeah, you'll find a neighborhood, Xj, I think. Did I do Xj? Xi, yeah. A neighborhood I'll find such that all of the Xi's or all of the X's are nearly independent. So nearly independent. Okay, everything here and here. So only dependence is here. Of course, I have to make it precise. What do I mean by nearly independent? But roughly that's the idea. And then you define these sums. B1, this B1, B2, B3 I'll define. B1 is just sum of the means. Double sum of these means, where I is running over I and J is running over corresponding neighborhood of dependence. B2 is or the covariance terms essentially, second mix moment terms. Again, double sum. B3 looks more complicated, but think of the situation when xi is exactly independent of xj's. Then this guy won't be there, and this just would be 0, and therefore B3 would be exactly 0. So when they are nearly independent, B3 should be small. However, if you want to make it too small by making these things too small, B1, B2 would become big. So there is a trade-off that has to be handled here, okay? So the idea, the result of Aratia, Goldstein, and Gordon is that the sum of the dependent Bernoulli and the sum of the independent Poisson is bounded by this linear combination of B1, B2, and B3. So as long as you can keep B1, B2, and B3 under control, you can have a bound on this total variation distance. And note that from the previous slide, this total variation distance between this guy and that guy, these two, is precisely this one in our notation. And all now we have to do, we have to bound B1, B2, and B3 separately. And as you will see, B1 and B2 won't be difficult here. I'm not going to write the details, but if you write what is B1, what is B2, and again, if you don't do it at 8 p.m. in the evening, you will be able to do it easily. It's not hard, okay? B3 is a bit more complicated, it looks complicated, but essentially it will come out of some mixing property. You're saying that, these two are nearly independent, which is basically some mixing property, okay? So this is the idea of the rest of the proof, B1, B2, B3. Choose Bi to be some neighborhood depending on n of I, and optimize to get Mn star equal to Ln. What do I mean by optimize? So as I said, there is a competition between B1, B2, and B3. It so happens that B1 and B2 has the same bound, and B3 has a different bound, and these two are competing with each other. So you optimize, made them equal, that's it. It's very easy. And then you get the Mn star, which is Ln. By the way, what is Ln? Ln was that same Ln that came up in the rate of convergence, Ln over n. And this is strictly lower than log n. So B1 can be bounded easily. B2 also reasonably easily, but it needs some mixing property again. And B2 doesn't really need the mixing property in the full strength, but B3 does need the following exponential mixing property of the AIs. This is the answer to Sandeep's question. First, Philip proved it in Duke Math Journal paper, and then Galambus wrote it in a probabilistic way. Philip's way of writing was very tedious. So this is how Galambus wrote it. I'm quoting Galambus actually, lemma 2 of Galambus more precisely. There exists a C and a theta such that the point is this. If you have A1, A2, AM, let me draw a picture here. So you have A1, A2, say A3. And here you have A3 plus N, A3 plus N plus 1, and so on. This block is close to be independent of this block, approximately, in an exponential fashion. So that's what exponential mixing. So in particular, it's exponentially ergodic also. Yeah. Yes, intuition is that, okay, the intuition is if you look at the maps, if you just look at A2, say, and try to see how dependent they are, you will see that already there are, A2, A1 is already not, okay, they are dependent, but it's going fast. Yeah, that's the intuition. So if you go a bit farther, in some sense, see even A1 and A3 say, if you try to brute force calculate the dependence and try to calculate this thing, you will see that they're already, this thing is already going to be small, this distance. So yeah, that's why. So it just comes out of the calculation. Okay? It's under the Gauss measure. Under the Gauss measure. Everything is under, this P is the Gauss measure, by the way, I should have said that. P is the Gauss measure. Thanks for pointing that out. Okay. Okay, so a remark on the proof is the referee, who I have a suspicion who he is, but I'm not going to say that, said that apparently this also gives a similar bound, and I think so. It gives a similar bound. Proof length would be similar, except that we haven't really checked the rates, but my guess is that the rates would be pretty similar. Okay? So there is another way to do it, avoiding the work of Aratia, Goldstein, and Gordon. Okay, so some consequences and future work. Quickly, one consequence of the extremal point process convergence, along with theorem 3.1 of Davis and Singh, which is actually a paper in time series analysis, okay, is that central limit theorem holds. Since these are regularly varying, it converges, however, after centering and scaling to a one stable random variable, which is positive. So the beta is, if you know what it is, the asymmetry parameter is 1. So it's a purely positive stable random variable. This actually recovers a result of Samur. This came out in Transactions, who proved it using brute force method. Yes, depends on how the regularly, see here the regular variation was exactly 1 over n with a constant. If you have a slowly varying function here, then something else comes up there. Because there is no the slowly varying function is 1 asymptotically, and therefore it's, yeah, that's a good question. If you go back to Feller, that's what happens, yeah. Or Paul Levy or whatever, yeah. Okay, so a quick number theoretic socialism is that if you choose a random number according to uniformly at random, not according to Gauss measure, look at the expansion, look at the fraction of how many of them are, say, 2 mod 7. So how many of them look like 7k plus 2? This fraction, all these fractions are actually equal in probability or in distribution, okay? So regular continued fraction is egalitarian towards all classes, all residue classes. That's all this means. This can be proved directly, but can be also proved to the point process convergence. You have to change the measure, and that needs some work, but it's not hard. Okay, geodesic flow or modular surface, I'll just skip this slide. So there is something called geodesic flow or modular surface. I don't want to talk about it, what it is, but for that, there is an extreme value theory result by Polycott. He is a very famous algorithmic theorist. Our work quickly yields a rate of convergence in Polycott's result as well. And this is an important quantity in hyperbolic geometry and number theory. And apparently the maximum, Anish tells me, has some number theoretic interpretation, which I don't know. Don't ask me, ask Anish. Okay, so I think there are many future directions, and a lot of things can be done. And this is sort of like, may sound like preaching, but I like to invite all of you smart people to try to pay your attention to this field, which is reasonably new. And this is the paper in the archive. Thank you very much. I'm thanking ICTS and TIFR because we did some work in this institute. Yep. Sorry for taking extra time, Raju.